Good morning. My name is Balitsky. I come to you from Ghent University, Department of Civil and Coastal Engineering. And today I want to talk about wave energy. Now, wave energy, you might ask. What is it and what does it do? Well, simply put, it is the conversion of the mechanical motion of the waves created by the blowing of the wind on the surface of the ocean into useful electricity. And here we have a schematic of the whole process. So let me walk you through it. On the left we have a picture of a wave, but in order to convert the motion to useful electricity, we need something called the wave energy converter, which is basically a machine which takes the mechanical energy of the waves and converts it to electricity. However, the story is not so simple, as each device is too small to produce this electricity in an economical way. Therefore, on the right, you see something which is called a WEC farm, which is basically an agglomerate of these devices that enables scaling effects, which then eventually serve to reduce the cost of electricity produced. Finally, on the bottom, we have what we hope is a successful result. That is clean electricity from the motion of the ocean, which will go to power your home sometime in the near future. So, why do we model wake farms? As I mentioned previously, the answer is economics. Because each device is too small to economically produce, we need to put many of them together. Unfortunately, the story is not as simple, because if we place many devices together, we cannot simply add up the power production of each isolated one because of things called hydrodynamic interactions. What these are is basically the influence of each individual device, such as the ones that you see here, on each other. This modification in the wave field affects the performance of each device and also affects the surrounding wave area in what is termed the far field effect. Now, of course, each individual process in this whole step is a complicated matter, and in order to understand the whole process, it takes more than one research group or indeed university to model the entire chain of wave energy conversion. What is our focus then? Well, here at Ghent University, we are interested in numerical modeling and physical modeling, and with numerical modeling, our focus of our group is on model coupling. So what we do to solve this problem is we take the results from a high resolution but computationally expensive model into a lower resolution but a much faster one. In our case, the model you see on the left is called NEMO. It is a boundary element method, a kind of solver for the motion of the devices. And on the right, we have our own in-house wave propagation model called MILEWAVE, which has been developed at Ghent University Coastal Research Group over a period of 20 years. So here we see the results on the left from the boundary element method, which are then coupled to the picture on the right, which is the wave elevations from a wave propagation model over a realistic coastline. What we see in the red and blue zones on the right-hand side image is an augmentation and reduction of the waves. Why are these important? Well, a modification of the wave field can in turn influence other sea users such as fishermen, such as coastal structures, other wave and wind energy projects, etc. Okay, and in my final slides of this presentation, I will show you an actual result of a hypothetical study we recently performed with wave energy converter farms. So here, we use Japan as an example because it is one of the countries at the forefront of wave energy development with a large population close to wave resources. So what we have done is we've modeled this small area, which you see at a small scale, or the large map scale on the left, and at a larger scale on the right. We have taken wave data from a nearby buoy, and we have run our coupled model over the area you see in the yellow box. So here's the result for this entire area. What you see here is a map of the wave elevations, and as we go from the right, which is offshore, to the left, which is onshore, we see a reduction and modification of the wave field by the presence of the 50 wave farm, which you see in the 10 red boxes in the center of the image. In my final slide, I will show you in detail this reduction and augmentation of the wave energy. So the red and the blue show you the positive and the negative influences, and sometimes the difference can be as large as 30%. Well, in the case of wave energy projects, that can be the difference between a successful project and an expensive failure. We hope that the research performed at Ghent University will bring more of the former and avoid the latter. Thank you for your attention and have a great day.